Hey guys, so apparently the reason I didn't previously record a chapter 6 part 1 was because it is very long. So whenever you need to pause, you just go ahead and do that and come back later. Just jot down where you stopped. Okay, so throughout this chapter, we're going to talk about sodium chloride a lot just because it has lots of real world applications and it's something that's in like everything that we eat, pretty much. Okay, so some other things we're going to be calculating. We can calculate how much iron is in iron ore. We can calculate how much chlorine is in chlorofluorocarbons, which is, part of the reason the ozone layer isn't what it used to be. So, first thing we're going to talk about is mass or conversions with that. And then we're also going to talk about conversions with what we call Avogadro's number. So it goes through just canceling units again, just basic conversions. Remember, whatever unit is here, that's generally what goes down here. They cancel, then we've got our new unit, it goes down here, they cancel, and we just keep going until we're to the place we want to be. Okay, luckily though, these have like an end point generally that's much sooner than our conversions in chapter 2 were. So we are going to use conversion factors like dozen, but we don't call it dozen in chemistry, but dozen is just something that we count with in the real world. So in chemistry, we use a different number, and moles is what that's referring to, and that's always going to be equal to 6.022 times 10 to the 23. Now this is for, really it's for anything, but in chemistry we use it for particles. Now, particles can be several things. They are molecules, atoms, formula units. Remember, those are for ionic compounds, the smallest piece of an ionic compound, and also ions. Okay? So sometimes we break substances apart and they're broken into ions, and that is very similar. Okay, so here's just everything that we're going to do in this chapter. We are going to cover half of this chapter, more than, in this one video. So I told you it'd be long. Oh. What happened? I don't know what happened. Okay. For some reason, we skipped a whole bunch. Okay, so here, we're back to the next slide. So this number is 6.022 times 10 to the 23. It is called Avogadro's number. Okay, Amedeo Avogadro is the one who is responsible for coming up with this number, and so he got to name it after himself. We will refer to him in some other chapters as well with different things, but they're all going to correspond to the mole. Now, like I told you before, we're going to use Avogadro's number for particles, but it could be used for anything. It could be used for marbles, sand, elephants, whatever we want to use. Okay? So, because atoms are so very tiny, that's why we use it for atoms specifically. Even like grains of sand are really too big for us to use moles for counting them, because the Sahara Desert only has about several moles of sand. The Sahara Desert is the biggest sand desert in the world, so we need to go smaller, which is where we get our atoms from. Okay, about 22 pennies pre-1982 era-ish. That would have been 1 mole of copper atoms. Because helium's a gas, it does take up more space. Okay, so a mole of helium atoms is about 2 balloons that are inflated. They are large. Okay, and this is just a definition. We do use this definition occasionally, but I don't generally ask you to tell me the definition. It does go back to carbon 12, so that's important from this. Carbon is one of the most abundant things that we have on Earth, and carbon 12 is the most common type of carbon. So here we are equating a mole to the number of atoms in exactly 12 grams of carbon 12. Okay, so here they're doing the conversions. I'm just going to jump right in. Remember, the conversion unit we're using is 1 mole is equal to 6.022 times 10 to the 23, and that's for particles, whatever particles we have, whatever particles they're asking for. Okay, for now, they're just going to be asking for elements. In a little bit, we'll transition to compounds. Okay, so they give us 1.1 times 10 to the 22 atoms of silver. And they ask, how many moles is that? So because I know that atoms are particles, I'm going to put atoms of silver down here. That way they cancel. Remember, the goal is that these two cancel out. And then that's always going to be equal to 1 mole of the same substance. Again, it's always equal to 1 mole. This 1 mole piece doesn't change. Okay, in this conversion, if I have Avogadro's number, that is 1 mole of atoms. Okay, so my atoms cancel. Great. Now we need to calculate it. Now, depending on how you're doing calculations, if you're not using that EE button on the calculator, you're going to need to put this bottom part in parentheses. Okay, otherwise you won't get the correct value. So I'm going to type 1.11 times 10 to the 22. Again, I use the EE button. That means times 10 to the, but if you're not comfortable using that or you haven't used it before, it's okay. Just use the little exponent caret button with the times 10. Again, though, if you're using that functionality of your calculator, you're going to need to put that bottom number in parentheses. Okay, when we do this, you should get 0.018 moles of silver. Okay, also while we're here, sig figs do matter. So we're going back to sig figs. Remember, as far as sig figs go, this value here, this number, it's a conversion factor and it's a constant. So we do not care about the sig figs and that they're unlimited. We need to look at how many they gave us. So this problem gave us 2. Therefore, we keep 2. All right, now we're going to go the other way. So we're going from moles to atoms. They want to know how many gold atoms there are. So we have 8.83 times 10 to the negative 2 moles of gold. Now, since moles is given, moles needs to go on the bottom. And then Avogadro's number goes on top. Again, it's always equal to 1 mole. Now, you can put the multiplication in parentheses, but you do not have to. You have to put it in parentheses when it's on bottom. All right, so this one has 3 significant figures. I get 5.32 times 10 to the 22 atoms of gold. Okay, please let me know if y'all have questions. Okay, so now we're going to go to dealing with masses because obviously these large nails in a dozen don't weigh the same amount as these small nails do of a dozen because the big ones are larger. So we use mass to compare them. So a mole of sulfur is equal to the mass of sulfur on the periodic table. And a mole of carbon is equal to the mass of carbon on the periodic table. Now, this textbook rounds all their masses from the periodic table to the hundredths place. If you are not comfortable rounding to the hundredths place, that's perfectly fine. Keep all the values on the periodic table just as they are when we're doing the math. Okay, I will be using them rounded to the hundredths place. Okay, so an atomic mass unit, which we have been talking about, that's 1/12 of the mass of a carbon-12 atom. Okay, but remember, we're trying to solve a mole, not for one atom, but for Avogadro's number of atoms, 6.022 times 10 to the 23. So that means that 1 mole of copper is equal to the mass on the periodic table. And we call this value the molar mass. So we were using the term formula mass at the end of chapter 5. Okay, molar mass is pretty much the same thing, except it's grams per mole instead of AMU like it was in chapter 5. So 1 mole of an atom is equal to its molar mass. Whatever that mass is on the periodic table, that's what it's equal to. So I'm going to write 1 mole equals molar mass. And then normally I say this is from, and I abbreviate periodic table PT because it's kind of long. Okay, it's still equal to Avogadro's number. It doesn't matter what the compound or element is, but it is different masses because every element has its own mass. All right, so jumping right in. On these, we're not paying attention to atoms or molecules or any kind of particles. They give us grams, they ask for moles. So we have these two conversion factors right now. So 1 mole is equal to molar mass, and 1 mole is equal to Avogadro's number. Okay, so because it didn't say anything about particles, I am only going to use my molar mass one because that'll get me to moles. So we're going to do 57.8 grams of sulfur, and then grams of sulfur goes down here. 1 mole of sulfur goes up here. Again, it's 1 mole, so please make sure you're paying attention to that. So sulfur on your periodic table, I believe, is 32.066. But I'm going to use 32.07 grams because I told you they're going to round to the hundredths place. Okay, remember if it's on bottom, we divide. So I'm going to do 57.8 divided by 32.07. And I get 1.80 because we're at 3 sig figs moles of sulfur. Okay. Then we're going to do it the other way. It's still just moles and grams, and also it's still sulfur, so that's nice. So I have 2.78 moles of sulfur. 1 mole of sulfur is our same molar mass because it's sulfur, 32.07, and this time we're multiplying because we're on top. I get 89.2 grams of sulfur. Okay, now we're going to put both of them together. So in order for us to use both conversion factors, it's got to talk about particles, in this case atoms, and it has to talk about grams, some kind of mass. It could talk about milligrams or kilograms. Those are also common masses that we use in science, but it has to say grams or mass, something along those lines, and some kind of particle. All right, so notice it says how many aluminum atoms are in an aluminum can that has a mass of 16.2 grams. Again, it's aluminum. So we go to our periodic table, we look up aluminum, and you should see that aluminum is 26.98 grams per mole. Okay, grams cancels. I want to cancel them here because we've got more than one step because I don't want moles, I want atoms. So we need to go again. So 1 mole of aluminum is equal to 6.022 times 10 to the 23 atoms of aluminum. Okay, obviously that takes up a bit more space. So if you're writing large like I am right now, make sure you leave a little bit extra space. Okay, so again, you can put this in parentheses if you want, but it's not necessary unless you're dividing. I get 3.62 times 10 to the 23 atoms, because our moles cancel, of aluminum. Okay, before I move on from this, I do want to be clear. Sometimes y'all miss the times 10 at the end of your calculator with the exponent. You absolutely need that part. If you're multiplying by a value with 23 extra zeros, essentially, or extra places than your number originally has, we need to make sure that we're accounting for that in our answer as well. Okay, so if you're missing a times 10 to the something and you multiplied by times 10 to the something, you need to go back and check your calculator, because atoms, there should be a whole lot of atoms. Pretty much always. Okay, if we're going the other way, It gives us helium atoms. It wants mass. So I do 1.23 times 10 to the 24 atoms of helium. So Avogadro's number goes up down here because I'm trying to get rid of atoms. All right, and helium is 4.0, so I'm just going to write 4 grams of helium. Okay, again, atoms cancel, moles cancel. If you're using a regular calculator or you don't know how to use the EE button, make sure that you put the bottom in parentheses. And I get that this is 8.17 grams of helium. Okay, if you need extra practice, please let me know. Reach out. I've got plenty. Okay, then we look at compounds. Remember, for compounds, we were finding the formula mass. And just a little bit ago, I said formula mass and molar mass are pretty much the same thing, except that was just for elements. For formula mass and molar mass of compounds, they're going to be the same value. Okay, we're going to find the mass from the periodic table by adding them all up. But right now, we're going to do the number of molecules. So these are still particles, but we're just using compounds. For molar mass, that is the grams per mole. It's equal to the formula mass of the compound in AMU. So basically all we're doing is changing out that atomic mass units for our grams per mole. And it's still equal to 1 mole because per means 1. All right, we're just going to jump right in. We've got moles of water. It wants grams of water. So 1.75 moles of H2O. 1 mole of H2O goes down here. Okay, if you want to add up the mass beforehand, that's fine. But I've got 2 plus my 1.01, which is my hydrogen, plus 16. So this is 18.02 grams of water. Moles cancel. We multiply. And I get 31.5 grams of water. Okay, so it's not so bad. It just has that small additional step of making sure you add up the mass from the compound. Okay, so now we're going to find the moles. It wants the moles of NO2, which is nitrogen dioxide, from 1.18 grams of nitrogen dioxide. So grams of NO2 goes down here. 1 mole NO2 goes up here. This is how I generally fill this in because I don't generally know the mass right off the top of my head. I need to calculate it. So I fill in my units. You can go ahead and cross them out. Then you can fill in your number, which is 46.01 because 32, which is 2 oxygens, plus that 14 is 46. So this time we're dividing because the 46 is on bottom, and I get 0.0256 moles of NO2. Okay. Notice they put it in scientific notation. It's okay to do that if you want to leave your calculator in that mode, but you don't have to. This is the same value, 2.56 times 10 to the negative 2. But I just write it however my calculator shows generally. Okay, now we're going to add in molecules. It's the same process, except now we're using both mass and Avogadro's number. No big deal, same as it was with elements. We're just adding that additional step of finding the formula mass. Okay, so we have, what is the mass? Ooh, didn't mean to cross it out. Of 4.78 times 10 to the 24 NO2 molecules. So 4.78 times 10 to the 24 molecules. Okay, now it is very important that you're paying attention to our compound because we're going to have to find the mass of that. Because molecules was given, I need to divide by Avogadro's number. And that's 1 mole of NO2. 1 mole of NO2 is equal to the molar mass, which in this case we've already found is 46.01. Okay. Again, put Avogadro's number in parentheses. I get 365 grams NO2. And that was more than 1 mole, at least, because we had a different exponent than we did in Avogadro's number. So really it's more like more than 10 moles. So this should make some sense. It's not quite 10, but pretty close. Okay, and then we could go the other way as well, same as we were doing with elements. So I've got 3.64 grams of water. I've already found the molar mass of water to be 18.02 grams in 1 mole of water. And then in 1 mole of water, I have 6.022 times 10 to the 23 molecules. There is no abbreviation for molecules, y'all. So don't abbreviate it moles. It's not moles. I get 1.22 times 10 to the 23 molecules of water. Okay. Again, I've got practice sheets. Most of them, though, are mixed, not just single elements and single compound ones. But I have a couple. Okay. Now we're going to get to comparing elements in a compound. So this is like a clover has 3 leaves, a 3-leaf clover does. So for every clover, there are 3 leaves. If you were asked how many leaves there were, you can multiply how many clovers you have by that 3 and to get a total number of leaves in your amount of clovers. Okay, we can do the same thing with atoms in a molecule. So I have 2 atoms of oxygen in 1 carbon dioxide. That also means I have 2 moles of oxygen in 1 mole of carbon dioxide. Okay, so this is going to be very important. This is a mole ratio. We're going to use this a lot in chapter 8. Not necessarily just elements in a compound, but compounds and compounds, or elements and elements. But very important, we're going to continually use this. So just like a spider has 8 legs, a chair has 4 legs, 1 water molecule has 2 hydrogen atoms, but 1 water molecule also has 1 oxygen atom. Okay, and this is an oxygen atom, not a 0. What is going on? Okay, it did that thing again. How nice of it. We're almost back. Okay, there we are. I don't know why it keeps doing that. I'll keep my arm off the laptop. All right, so we have 1.7 moles of calcium carbonate, and it wants to know how many moles of oxygen there are. So you need to look at the subscript. So in 1 calcium carbonate, there are 3 oxygens. So all I do is multiply my 1.7 times 3. And I get 5.1. 5.1 moles of oxygen in 1.7 moles of calcium carbonate. Let's do another one. I've got 1.4 moles of sulfuric acid. And they, again, want to know how many oxygens. So I've got 4 of them. So in 1 mole of that, I have 4 moles of oxygen. And I get 5.6. Now, if they would have asked how many moles of hydrogen, instead of multiplying by 4, I would have multiplied it by 2 to get 2.8 moles of hydrogen. Okay, and then sulfur, if they'd asked for sulfur, it had just been 1 mole of sulfuric acid to 1 mole of sulfur on top, so it would have been the same number because there's just 1 sulfur in that sulfuric acid compound. Now, we can use this mole ratio piece in the middle to go back and forth and find how much of a missing or some mass of an element in that total compound. There is also going to be another way to do that in part 2. Okay, so this is a big compound, C10H14O, carvone. They give us the mass of carvone and they want the mass of carbon. So we're going to start with our mass of carvone that they gave us. I'm going to write the compound out. Okay. I know that the mass of carvone has to go down here. And that's 1 mole of it. Again, it's always 1 mole as long as we're not in the mole ratio. Okay. In 1 carvone mole, there are 10 moles of carbon because it's asking about carbon. And then we go back, 1 mole of carbon is 12.01 grams of carbon. Okay, yes, I did leave this spot blank. It's because it requires a calculation when the 12.01 did not. I could just pull that from the periodic table. Okay, so I am doing the addition, and I get that carvone's mass, molar mass, is 150.24 grams. Okay, so I'm going to do 55.4 divided by 150.24 times 10 times our 12.01. So I get that it is 44.3 grams of carbon in 55.4 grams of carvone. Now that should make sense because while you were doing the molar mass addition, just the carbon alone weighed 120 grams of this 150. So it should be about, what is that? 3 or 4/5 the amount of this. So 80%, and 44 out of 55 is about 80%. So that looks like a good value. Okay, now while we're going to have maybe 1 or 2 questions on this, now mole ratios are going to become more of a thing, so that's why you need to get used to them, okay? So in this one, I've got sodium bicarbonate. How nice of them. It gave you a formula, and it wants us to determine the mass of oxygen. So 5.8 grams of our sodium bicarbonate, which is just baking soda. Okay, I'm going to put my grams of sodium bicarbonate down here, and 1 mole. Okay, in 1 mole of sodium bicarbonate, I have 3 moles of oxygen, and then 1 mole of oxygen weighs 16 grams of oxygen. Now, some of you may be thinking, but in chapter 5, she told us oxygen was diatomic, which yes, it is, but oxygen is not alone. It is a piece in this compound. So because it's not alone, it's not a diatomic molecule. It's just a single atom. Okay. So sodium's 22.99, hydrogen's 1.01, carbon is 12.01, and our oxygen is 48 total. So this leaves 84.01 grams. I get 3.31 grams of oxygen. Oh, that's not the right sig figs. 3.3 grams of oxygen because it only gave us 2. Now again, oxygen was 48 grams of this 84, so that is more than half, so 3.3 is more than half of that 5.8. So that's kind of how you can guess and like make a check that yes, it is correct or at least close because our percentages are about the same. Okay, here's one more. If you need to work it, I would say go ahead. You can pause. I'm not going to work it. If you need help, just reach out. Let me know. All right, that's it. Y'all have a great day.